Vertical line test. The vertical line test is a handy way to think about whether a graph defines the vertical output as a function of the horizontal input. Imagine drawing vertical lines through the graph. If any vertical line would cross the graph more than once, then the graph does not define only one vertical output for each horizontal input. Horizontal line test. Once you have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use the horizontal line test. Draw horizontal lines through the graph. If any horizontal line crosses the graph more than once, then the graph does not define a one-to-one function. Evaluating a function using a graph requires taking the given input and using the graph to look up the corresponding output. Solving a function equation using a graph requires taking the given output and looking on the graph to determine the corresponding input. Example 9. Given the graph of f of x, A, evaluate f of 2, B, solve f of x equals 4. A. To evaluate f of 2, we find the input of x equals 2 on the horizontal axis. Moving up to the graph gives the point 2, 1, giving an output of y equals 1. F of 2 equals 1. B. To solve f of x equals 4, we find the value 4 on the vertical axis because if f of x equals 4, then 4 is the output. Moving horizontally across the graph gives 2 points with the output of 4, -1 and 4, and 3 and 4. These give the two solutions to f of x equals 4, x equals -1, or x equals 3. This means f of -1 equals 4 and f of 3 equals 4, or when the input is -1 or 3, the output is 4. Notice that while the graph in the previous example is a function, getting two input values for the output value of 4 shows us that this function is not one-to-one. Formulas as functions. When possible, it is very convenient to define relationships using formulas. If it is possible to express the output as a formula involving the input quantity, then we can define a function. Example 10. Express the relationship 2n plus 6p equals 12 as a function p equals f of n if possible. To express the relationship in this form, we need to be able to write the relationship where p is a function of n, which means writing it as p equals something involving n. 2n plus 6p equals 12. Subtract 2n from both sides. 6p equals 12 minus 2n. Divide both sides by 6 and simplify. P equals 12 minus 2n divided by 6 equals 12 over 6 minus 2n over 6 equals 2 minus 1/3 n. Having rewritten the formula as p equals, we can now express p as a function. P equals f of n equals 2 minus 1/3 n. It is important to note that not every relationship can be expressed as a function with a formula. Note, the important feature of an equation written as a function is that the output value can be determined directly from the input by doing evaluations. No further solving is required. This allows the relationship to act as a magic box that takes an input, processes it, and returns an output. Modern technology and computers rely on these functional relationships since the evaluation of the function can be programmed into machines, whereas solving things is much more challenging. Example 11. Express the relationship x squared plus y squared equals 1 as a function y equals f of x if possible. If we try to solve for y in this equation, y squared equals 1 minus x squared, y equals plus or minus the square root of 1 minus x squared. We end up with two outputs corresponding to the same input. So this relationship cannot be represented as a single function y equals f of x. As with tables and graphs, it is common to evaluate and solve functions involving formulas. Evaluating will require replacing the input variable in the formula with the value provided and calculating. Solving will require replacing the output variable in the formula with the value provided and solving for the inputs that would produce that output. Example 12. Given the function k of t equals t to the third power plus 2, A, evaluate k of 2, B, solve k of t equals 1. To evaluate k of 2, we plug in the input value 2 into the formula wherever we see the input variable t, then simplify. K of 2 equals 2 to the third plus 2. K of 2 equals 8 plus 2. So k of 2 equals 10. B. To solve k of t equals 1, we set the formula for k of t equal to 1 and solve for the input value that will produce that output. K of t equals 1. Substitute the original formula k of t equals t to the third plus 2. T to the third plus 2 equals 1. Subtract 2 from each side. T to the third equals negative 1. Take the cube root of each side. T equals negative 1. When solving an equation using formulas, you can check your answer by using your solution in the original equation to see if your calculated answer is correct. We want to know if k of t equals 1 is true when t equals negative 1. K of negative 1 equals negative 1 to the third plus 2 equals negative 1 plus 2 equals 1, which was the desired result. Example 13. Given the function h of p equals p squared plus 2p, A, evaluate h of 4, B, solve h of p equals 3. To evaluate h of 4, we substitute the value 4 for the input variable p in the given function. A, h of 4 equals 4 squared plus 2 times 4 equals 16 plus 8 equals 24. B, h of p equals 3. Substitute the original function h of p equals p squared plus 2p. P squared plus 2p equals 3. This is quadratic, so we can rearrange the equation to get it equal to 0. P squared plus 2p minus 3 equals 0. Subtract 3 from each side. p squared plus 2p minus 3 equals 0. This is factorable, so we factor it. P plus 3 multiplied by p minus 1 equals 0. By the zero factor theorem, since p plus 3 multiplied by p minus 1 equals 0, either p plus 3 equals 0, or p minus 1 equals 0, or both of them equal 0. And so we solve both equations for p, finding p equals negative 3 from the first equation and p equals 1 from the second equation. This gives us the solution h of p equals 3 when p equals 1 or p equals negative 3. We found two solutions in this case, which tells us this function is not one-to-one. Basic toolkit functions. In this text, we will be exploring functions, the shapes of their graphs, their unique features, their equations, and how to solve problems with them. When learning to read, we start with the alphabet. When learning to do arithmetic, we start with numbers. When working with functions, it is similarly helpful to have a base set of elements to build from. We call these our toolkit of functions, a set of basic named functions for which we know the graph, equation, and special features. For these definitions, we will use x as the input variable and f of x as the output variable. Toolkit functions. Linear. Constant. F of x equals c, where c is a constant number. Identity. F of x equals x. Absolute value. F of x equals absolute value of x. Power. Quadratic. F of x equals x squared. Cubic. F of x equals x cubed. Reciprocal. F of x equals 1 over x. Reciprocal squared. F of x equals 1 over x squared. Square root. F of x equals the square root of x, which equals the square root of x. Cube root. F of x equals the cube root of x. You will see these toolkit functions, combinations of toolkit functions, their graphs, and their transformations frequently throughout this book. In order to successfully follow along later in the book, it will be very helpful if you can recognize these toolkit functions and their features quickly by name, equation, graph, and basic table values.